So here we go with 16.3, the circumference of a circle. And this may be one of the shortest lesson notes that we do all year. But I want you to, I can't remember if on your copy you have these 6 circles on there or not. If not, go ahead and draw in 6 circles. Try and make them the same size. You may even want to use your compass. That would be a good idea. And then what I want you to do is I want you to do kind of what you see here, where we've got a equilateral triangle, and then a square, and then we've got a regular pentagon. And then I want you to continue by trying to draw in a regular hexagon, octagon, and decagon. And you'll soon start to see, if you haven't already, even from these 3, that as the number of sides increases in our regular polygon, from 3 to 4 to 5 to 6 to 8 to 10, what happens to the perimeter? Doesn't the perimeter become closer and closer to C, which is our circumference? So as the number of sides increases from 3 to 4 to 5 to 6 to 8 to 10 to 12 to 15 to 20 to 100 to 1,000, you can see how the perimeter approaches the circumference. Never quite gets there, obviously, because we could always continue to add sides. But if we had an infinite number of sides, then that would be the circumference. Okay, so we're going to talk about this in the form of a theorem. And basically the theorem says the ratio of the circumference to the diameter is the same for all circles. And yes, this is leading you to that 2-letter word, which is actually a letter in the Greek alphabet, pi. Because pi, as you know, is the ratio of the circumference to the diameter for a circle, and it's the same for all circles. So we're actually going to prove that. So here we go. I've got 2 circles here, and you can see I've got 2 squares in here. These circles are not the same size, so we're going to be dealing a lot with similarity here, obviously. Okay, so E is the side length, okay, and E prime, or whatever you want to call that, is the side length here. N obviously is the number of sides. P is the perimeter, and C stands for circumference. Okay, well obviously we know that we have radius, radius, radius prime, so we can see how we have these triangles are similar by SAS, right? And if they're similar, then by SysDip, we know that E over R is equal to E prime over R prime, right? Okay. Well, if we multiply the number of sides in, that's not going to change things because we've just multiplied by n to both numerators of an equal, of a proportion. So 2 equal fractions. So that's going to stay the same. Okay. Well, isn't the number of sides times the length of one side, 4 sides times the length, wouldn't that be the perimeter? And same for this one, right? So NE can be replaced with P, and NE prime will just replace with P prime. So we still have a proportion here. Okay. And we know that as the perimeter is going to approach, as a limit, the circumference as the number of sides increases. So P over R is going to approach C over R, and P prime over R prime is going to approach C prime over R prime. Okay. So if we know this is the case and this, then we can say that these are equal, right? Okay. Can't we also then, if these are equal, multiply both denominators by 2? So it becomes 2R and 2R prime. So we have C over 2R is equal to C prime over 2R prime. And we just use pi to represent C over 2R. So pi is equal to C over 2R. Well, isn't 2R the same as diameter? Sure is. So if I cross multiply here, I get C is equal to 2R pi, or 2 pi r, however you want to say it. And at the same time, circumference is equal to pi times diameter. All right, so there you have it. We have proved that the ratio of the circumference to the diameter is the same for all circles. circles.